All right, so let's before we. So what we're doing today, we're doing the alternating series test, and then the ratio and the root tests. So before we do that, though, let's do a quick little recap of convergence tests so far. So what was the very first one that we did? Technique. Before that. Which one? Even before that. There was the...
Oh, yeah, the telescoping.
The telescoping series, right? So that was the one where you had the terms in the middle canceled out, right? So, you know, when you have something like 1 over n minus 1 over n plus 1, or the sum of, you know, I don't know, something like 1 over n times n minus 1, right? So this second one, it doesn't look like it's telescoping, but if you break it up using partial fractions, then it could potentially be 1, right? So those you can actually find the sum, right? So you just write it all out and then write the sum. Yes? Okay. Then the second one was what's the other one that we can find the sum of? Yeah, the geometric series. So the geometric series. So this one looks like sum c times r to the n, and then n equals to 0 to infinity, right? And so then what this is, it converges if what?
If r is less than the absolute value of r is less than 1.
Convergence, right? Mm-hmm. Converges. And if the absolute value of r is greater than 1, then it diverges. And we can actually find the sum, right, of this one using the formula that we had earlier, if it converges, right? Okay. Then after that, what did we do?
Comparison test.
Comparison test. Comparison test and the limit comparison test. Now, what's the difference between the two? So what tells you to use one or the other? So they're very similar, right? In both of them, you compare a similar series to the one that you're trying to find. The comparison test you do if it's easy to show the inequality you want, right? So if the inequalities go in the right direction with what you're trying to compare to, right? But the limit comparison test, you don't have to worry about it, right? So if you use the limit comparison test, if you want to compare, but let's say the inequalities are difficult. And especially, what are the most useful ones to compare to, typically? The
P series.
The P series, right? So that's one that you always know whether it converges or not, right? You have the P series, 1 over n to the P. So it's very common to compare to a P series or a geometric series, right? Okay. And then after that, we did the integral test. So you have the integral test, and when do you use this one?
Oh, decreasing, positive.
Positive,
Continuous, yeah.
decreasing, and f is easy to integrate, right? So all those things, and you have to check all those. So the integral test could potentially be a lot of work because you have to show that it's always positive, you have to show it's decreasing, and then you have to be able to integrate it. So, but if it's a function, like you look at it and like, oh, if that was a function of x, I can integrate that, no problem. Then that would be a good way to go. You know. Okay, and then what else? And well, that's it, right? That's it. Okay, so then we land where we are now. All right, so you know, in a way, you know, you learn all these techniques. It's similar to integration, right? You have to know, take a look at the series. Which one do I use? What does it look like? And again, with practice, it gets easier. So, okay, so let's take a look at the alternating series test. Okay, so suppose you have the series, the alternating series, looks like this. You have -1 to the n times a sub n. So this is alternating, right? +1, -1, +1, -1. So this series converges. I think actually your book calls this I'm not sure why, but I've never seen it called this, but it calls it the Leibniz test. But it's the alternating series test. Okay, so this series converges if both of the following are true. So 1, a sub n is monotonically decreasing, and the limit as n approaches infinity of a sub n is equal to 0. So if you take a look at the sequence without the alternating part, if that sequence goes to 0 and the sequence is decreasing, then it converges. Let me show you a little picture of what, well, I'll try to show you a picture. So the sequence is both decreasing and it goes to 0, right? And it's alternating. So let me draw a number line here. Let's say that 0 is right here. And then maybe I should, let me do, it doesn't matter really at all, but just so that it's for my picture to work out a little better. So I'm going to I just put a +1. Because I wanted my first one to be positive. But it has nothing to do with it doesn't affect anything at all. Okay, so if I, so on this plot here, I have, let me see here. Let's say this is a sub 1. So this is the first partial sum, right? So if I just add the first term of the sequence, then it is just a sub 1, just right there, right? Okay. Now, the next term, a sub 2, let's see. So a sub 2 is, let's see. I'll try to fit it in right here. Okay. A sub 2 is smaller than a sub 1, right? Okay. And then is less than a sub 1. And what else? It's also, it's alternating sign, right? So it's going to be negative, right? Okay. So that means that you're going to go back in this direction whatever a sub 1 is, right? Or sorry, a sub 2. So the distance from here to here, let's say, that's a sub 2, right? So you go back, so you're going to subtract that amount, so then you're over here, right? So this is going to be s sub 2. So if you add the first term of the sequence and the second term of the sequence, you would be, after the first term, you would be at a sub 1. Then you subtract a sub 2, which is smaller, so you end up right here. Does that make sense? Yeah?
Seems like we go back to 0.
No, but remember, a sub 2 is smaller, right? So a sub 2, I guess I should put it in absolute value, right?
Negative and small.
Right, because it's, yeah, so it's alternating signs, and remember, it's monotonically decreasing. So a sub 1 is bigger than a sub 2, which is bigger than a sub 3, which is bigger than a sub 4, and so on and so forth. So notice that what I'm plotting right here, this is the sum, right? So positive here, I add and I end up over here. Now the next one, a sub 3, is going to be smaller than a sub 2, but this time it's going to be positive, right? So like if I go over here, a sub 3, can it go past that red line?
No.
No, it has to be smaller than that red line, right? So let's say it stops right here. This would be s sub 3, right? Because now you're adding a number that's smaller than a sub 2. So you would end up somewhere around right here, right? Okay, then the next one, you add the next one, which has to be smaller than that one, right? So then let's say that is smaller. It has to be smaller than the green line. So that is s sub 4. So all of them have to keep going. So you're going one direction, then the other, and one direction, and the other. But you can never go past where you were before, because every single term in the sequence is always smaller. Does that make sense? So then it would make sense that if you continue in this way, you would keep eventually converge somewhere, right? Does that make sense? So if any of these two conditions aren't satisfied, then this is not necessarily the case, right? Because if it's not monotonically decreasing, then that means that if you look at this and you go in you can go past one of them, and you can keep going past in a bunch of different directions, right? And the second condition that it goes to 0, well, that means that it's eventually going to completely die out, right? So, okay, all right. So let's prove it. So let's see, proof / fun times. Fun times / proof. Okay. All right. So let's take a look at. We're going to take a look at the even and odd partial sum separately. So, separately. Okay, so so what we want to do is we're going to use the our favorite theorem that we've been using to prove almost every single one. What is it? No. No. What's the theorem that we use to prove almost all the tests? It starts with an M. No. We used it last time a bunch of times. No? The monotonic sequence theorem. Yeah. So if it's increasing and bounded, right? Or decreasing and bounded from below. Okay, so that's what we're going towards. So let's do. So we want to show that. So let's write down s sub 2. So s sub 2 is a sub 1 minus a sub 2, right? And then S sub 4 is a sub 1 minus a sub 2 plus a sub 3 minus a sub 4, right? So now let's say I want to write S sub 4 in terms of S sub 2. What would it look like?
S2 plus
S2 plus
A3 minus
A3 minus A4, right? Okay, but then what is, oh, not A3 minus A4, sorry. What do I know about, okay, so what do I know about A1 minus A2? That is positive, yep. And what do I know about A3 minus A4? Positive, right? How come? Why is it positive? Yeah, remember it's decreasing, right? So because the sequence A sub n is decreasing, then the next term is always going to be smaller, so you're always subtracting a smaller one, right? Yes? So far so good? Okay. What is
S2, right? Not Sn.
Yes. Thank you. Sorry about that. So what this means then is that, so this is S sub 4 is equal to S2 plus some number. So that means that it has to be greater than or equal to S sub 2, right? Yes? Okay. So if you keep doing this, then in this same way you get that S of 2n is going to be greater than or equal to S of 2n minus 2, right? So you just keep doing this over and over and over again, and then the same thing happens. So what does that mean? That means that, what does this imply? S of 2n is, what did we just show? Yep. Yeah, it's increasing, right? Isn't that one of the critical pieces of information that we need, right? So we need both increasing and bounded above, right? Okay. All right. So then, what is it bounded by? Is it bounded? How can I show that it's bounded? Let me see, I'll go back to the picture. What do you notice? What is the sum bounded by? You can see it in the picture.
0 and A1.
It's bounded by A1, right? Because A1 is the biggest one, right? And so then you're taking away smaller and smaller pieces. So the largest it could ever be is that very first term in the sequence, right? So S of 2n is bounded because S of 2n is less than or equal to a sub 1. Okay, so all right, so therefore S of 2n, S of 2n converges by the monotonic sequence theorem. Okay, so now this was just the even ones, right? So then we want to insert the odds in there. So if I take a look at the odd partial sums, so this is, I can write it as S of 2n plus 1. This is equal to, how can I write the partial sum up to 2n plus 1 in terms of S of 2n. What else is missing? So the left side is the partial sum of up to 2n plus 1, the 2n plus first term. this s of 2n goes up to the 2n term, so what's missing? Not a sub 1, a sub, 2n plus 1, right? So just that one extra term that's missing, right? So you go up to 2n and then you're missing the very last one. Does that make sense? Yeah? No? So left side is the partial sum of all the terms in the series from a sub 1 all the way up to 2n plus 1. That's what you want, right? S of 2n goes up to from 1 all the way to 2n, the sum, right? And this is the 2n plus, the very last piece. Okay, but what do we know about a sub 2n plus 1? What do we know about the limit as n goes to infinity of a sub 2n plus 1? Goes to 0. Why?
It's one of the qualifying things.
That's one of the assumptions, right?
Yeah.
This is one of the assumptions that we have. It's assumption number 2 that the sequence converges to 0, right? So since it converges to 0, then the limit as n goes to infinity of s of 2n plus 1 is equal to the limit as n goes to infinity of s of 2n, right? So that's it, right? So we showed the even partial sums converge, and then we just showed that the odd ones are converged to exactly the same thing, and so then it converges. Thumbs up? Okay. So let's do a quick example of something that, so here's a series that you guys already know. Did I tell you what this is called? This even has a special name. Did I tell you? Or no. It's called the harmonic series.
Oh, yeah.
But anyways, this diverges, right? Just how it's written right now, it diverges, right? We showed that already. Okay, but then let's say we make it the alternating. So let's say we give it that. So now it's alternating. So it's 1, well, negative 1 plus a half, minus a third, plus a fourth, minus a fifth, plus. Okay, so this is now alternating. So if I can show that the sequence, so the limit, well, let me do this. Let me erase that. All right. So we're going to use the alternating series test, AST. Okay, so the first condition is that it's decreasing, right? So A sub n is obviously decreasing, right? So what tools do we have to show that something is decreasing or increasing? There are two ways, right? We can either do the derivative, right? Remember? So derivative, or you can just show directly, right? That a sub n plus 1 is less than a sub n. This one is so obvious that we don't even bother with either of them, right? I mean, it's very obvious that one half is less than 1 and a third is less than a half, right? So, okay. So if it's really obvious like this one, then you don't have to worry about it. Most of the time you do. Okay, then the limit as n goes to infinity of the sequence 1 over n, that's equal to 0. And so then the series what? Converges by? alternating series test, right?
How come you only wrote 1 over n? Is it the whole function?
Because that's all you have to look at. You don't have to look at the alternating part, right? So if you go back to the test, you have the alternating part, right? The -1 to the n. And then you have but the only thing that you need is for the limit as n goes to infinity of the sequence a sub n to go to 0. So you don't look at the alternating part at that point. Thumbs up? Yep. So so basically, you have what was I going to say? So for a lot of the series, remember we have the divergence test. Actually, we forgot to write that one down. Now that I remember, that was like the easiest one. Remember? What does the divergence test say? It's the limit as n goes to infinity of a sub n is not equal to 0, then the series diverges, right? Ran out of space there. So you have to have the sequence in the series that has to go to 0, right? So what this last test says that if it's an alternating series, then as long as it's decreasing and the sequence goes to 0, then it converges, right? Okay. So remember, if you didn't have the alternating part and the sequence went to 0, does that mean that it converges? No, right? It means that it might converge. So if it doesn't go to 0, then it definitely doesn't converge. But if it does go to 0, then you still have to do more work to show that it converges. But if it's alternating, all you need is for it to be, for the sequence to go to 0 and have it be decreasing. Now notice that here I have that it's monotonically decreasing. That means that it's decreasing from the very, very beginning, right? But is that really, really, really necessary? No. What do you need? This is what we assumed here, right? But remember we talked about this earlier, that what's what really matters for convergence? Yeah, the tail end, right? The tail end has to converge, because if you take out a finite number of terms from the beginning, that's always just a number. So you can always take that out. For example, let's say you have a sequence that, hypothetically, let's see, let me draw a little picture. Let's say you have a sequence that when you draw a picture, it looks like this, right? Something like that. And so this isn't monotonically decreasing, right? But if you take a look after this point, it is, right? So if you take out, let's say you change it so that you start right here, this over here on the left side, that's just a constant, right? So let's call it some constant, because it's just a finite number of terms that you're just taking out. That's some constant. If this part on the right, on the tail end, let's say this converges, to some number, whatever it is, then the whole thing converges, right? Because then you would just be adding a constant. So although in the theorem we're assuming that it's monotonically decreasing, we can also extend that to show that as long as it's eventually monotonically decreasing, then we'll be okay. Yeah? Thumbs up for that? Any questions?
C to infinity, it's monotonically decreasing.
Well, C represents, let's say this is, I don't know, m or something, little m or something. But C, what I wrote down here as C is the actual sum itself of the numbers. So like, let's say this is 1, let's say this is, I don't know, 2, 3, 4. So C in this case would be 10. Like just that sum, whatever the sum is. Questions? Alternating series test? No? Okay. All right, so let's see. All right, so then let's do a couple of definitions and theorems. So a series n equals 1 to infinity is called no, hold on. Let's take out the called. Let's take out the is too. No, wait. Okay, a series converges absolutely if the series of the absolute value of a sub n equals 1 to infinity converges. If the series of a sub n converges, but the series of the absolute value doesn't converge, does not converge, then that's called conditionally convergent. So then the series n equals 1 to infinity converges conditionally. So which one is a stronger form of convergence? So we have absolute convergence and conditional convergence. Yeah, absolute, right? Just the words tell you. But so absolute convergence is stronger, right? Because it means that that you don't need those negative terms to take out and help you converge. So like the easiest example that you can look at is the one that we just did, right? If you take a look at these two series, so you take a look at this this series right here. This series converges, right? By the alternating series test, right? So it converges, it's a convergent series, but does it converge absolutely? Meaning if you get the absolute value of all of these terms, will it converge? Well, no, right? Because if you take the absolute value of this series on the right, then it's the series on the left. It's this one, right? But this one is divergent. That's the divergent harmonic series, right? So this series right here is convergent. So it converges conditionally. It's just a term. Oh. Sometimes I forget how to spell. Here, I'm bored. Okay, so we don't use them that much, but it's just something to keep in mind. Okay, so let's do a quick little theorem, mini theorem. Oh, shoot. All right, mini theorem, and then we'll do some examples. If the series of the absolute value of a sub n converges, then the series of just a sub n also converges. Okay. Dun, 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 dun. Okay, so let's see. All right, so let's do some examples. Let's see. I've got some examples here. So we already did the harmonic series. How about, let's see, sum -1 to the n 4n over 6n plus 1. N equals 1 to infinity. All right, so what do you guys think? So the first thing you should always do when you see a series is go with what your gut tells you and take a look and see, okay, well, what do I think happens? So what do you guys think? So if it's alternating, probably what you want to do is take a look for absolute convergence. Just if you were to take it out, what's going on there? So what's the first thing you check to see if something converges or diverges? The first check that's super easy. Yeah, the divergence test, right? So you just take a look at the sequence and see if it goes to 0. If it doesn't, then you're done, right? And for the alternating series test, you need to do that anyways, right? It's one of the things you need to check. So I mean, might as well get it out of the way, right? So the limit as n goes to infinity of 4n over 6n plus 1 is equal to 4/6, right? Or 2/3. And that is definitely not equal to 0, right? So this means that the series diverges by the divergence test, right? So you don't even have to look to see if it's decreasing or anything. I mean, the sequence doesn't even go to 0, so there's no chance. Nothing. Okay. Let's see. So how about, so let's do another one. Let's see. We've got n equals 1 to infinity of -1 to the n squared over n cubed plus 1. All right. So what do you guys think about this one? What does your gut tell you? Go with your gut. What is your gut?
Same thing. Divergence test.
So we try the divergence test, right? So we take a look. We go, okay, the limit as n goes to infinity of n squared over n cubed plus 1. What is that?
Goes to 0, I think.
It's equal to 0, right? So the degree of the denominator is greater. So if you did L'Hopital's rule a couple times, it would show that it goes to 0. So what does this tell you? You should...
Do another test.
Well, yes. Yeah, I mean, well, yeah, you should continue, right? So do a test. So it might converge, it might not converge. Since it's alternating, then you should try the alternating series test. So this is actually part 2 of the alternating series test, right? So we just showed that, so check. Now we just need to show that the first part, which is that the sequence is decreasing, right? So how can we do that? Would it be easier to show using the derivative or directly?
I'd say just directly.
Because, so notice if you were going to show it directly, you would have to plug in, replace n with n plus 1, and then set up the inequality and see if you can make it obvious, basically. But when you have high powers, I would probably say that's not the best idea. So let's do the derivative. The derivative is simple enough to calculate. So the function in terms of x that would define the sequence would be x squared over x cubed plus 1, right? So the derivative of that is equal to 2x times,
times x cubed plus 1.
yep, minus x squared times 3x squared, right? All over x cubed plus 1 squared. So if I simplify this a little bit, let's see, I have 2x to the 4th minus 3x to the 4th, right? So that's going to equal to 2x minus x to the 4th over x cubed plus 1 squared, right? So what do I have here? Let's do let's take out an x, 2 minus x cubed. So what do I want this to show me? That is, well, that it's negative, right? So this is negative, right? For what?
X value that's greater than or equal to 1.
Not 1, right? Because if x is equal to 1, this is 2 over positive, so that's positive. When does it become negative? It's basically, so this x outside, that's going to be positive, right? And remember, since you're only talking about values of x greater than or equal to 1 to begin with, right? So you don't even have to worry about negative x values. You're only worrying about positive x values. So this x on the outside is always going to be positive. When does this, is this, yeah, at cube root of 2, right? So when x is greater than or equal to the cube root of 2, then this becomes negative, and then it becomes negative for all values after cube root of 2, right? Does that make sense? Yeah? You guys with me? Thumbs up, action. Okay, so this is what we were talking about, that you know, it's not decreasing starting at 1, right? But after cube root of 2, which is, so for n values of n, you know, for after 2 or greater, then it's decreasing, and that's fine, because that one term in the series won't affect the actual whether it converges or not, right? Yeah. Okay, so then so the series converges by the A, S, T, T. All right. Questions? Questions? No?